Welcome to the Walton Pi final exam review for Calculus 1. So we're going to cover everything starting at functions, going through limits, talking about derivatives, talking about some related rates, optimization problems, jumping into antiderivatives, integrals, and we're going to finish up with the net change theorem and U-Substitution. I'm going to go very fast through a lot of these topics, so if there's any topics that you don't understand, please check out one of my other videos or the test reviews that I covered on these topics previously, because those will go more in depth because there's just frankly a lot more time. So without further ado, let's just jump right on in and start plowing our way through all of these different topics. So to get started, let's talk about functions. So which of the following are functions of x? So which of these are functions of x? We got a y equals 13x minus 17 if x is not equal to 7. We have y equals sine x minus cosine x. We have x equals the square root of y. D, we have y squared equals x. And then E, that's not an E. E, we have y cubed equals x. Pause the video and try and figure out which of these are going to be functions. So it turns out that A, B, C, and E are all functions. All of those are going to be different functions. If we go through and graph them, none of them fail the vertical line. The only one that fails is D, because that's this function which automatically fails that vertical line test. Alright, let's now move on to function composition. So if we have f of x equals x cubed minus 7x, we got g of x is equal to cosine of x plus 7, and we have h of x is equal to 7 plus e to the x squared. What is f of g of h? Okay, so f of g of h, that is f of g of h of x. I think that's the right number of parentheses. So that'll be f of g of 7 plus e to the x squared. So now everywhere there's an x in g, we replace it with 7 plus e to the x squared. So this will be f of cosine of 7 plus e to the x squared plus 7. So this is f of cosine of 14 plus e to the x squared, which is going to be cosine of 14 plus e to the x squared cubed minus 7 times cosine of 14 plus e to the x squared. There you go. That's function composition. You can also have function multiplication, function addition, function division, all of those different things. Okay, our next one, we are going to be talking about inverse functions. So, well, I guess first we should probably quickly touch on the unit circle. So the unit circle connects with trigonometry. We have a bunch of different angles, and each of these angles has some different values. So this one is theta equals 0, and it's the point 1, 0. This next one is theta equals pi sixths, and it's the point root 3 over 2, 1 over 2. We have theta equals pi fourths. This is root 2 over 2, root 2 over 2. We have theta equals pi thirds, and this is the point 1/2 root 3 over 2. And then this angle here, this is theta equals pi halves, and it's the point 0, 1. And all of these are in the form cosine theta, sine theta. And through and be able to generate the rest of the circle using this. And this is also a good time to remember the different ratios of sides. So sine is opposite over hypotenuse, where we have some angle theta, we have opposite, adjacent, and hypotenuse, and you're trying to figure out what those different things are. Sine is opposite over hypotenuse, cosine is adjacent over hypotenuse, and tangent is opposite over adjacent. All right, let's now move on to inverse functions. Okay, what is sine of inverse tangent of x? And let's get a few other ones as well. Let's see, we got what is secant of cotangent inverse of theta. Let's not do theta. Inverse cotangent of y. We got cosine inverse of cosine of 3 pi over 2. And we got cosine of cosine inverse of 4. Okay, go ahead, pause the video, and figure out what each of these are. So, for this first one, sine of tangent inverse of x, the way that I would approach these is I would draw a triangle, because tangent inverse of x, that means that we have tangent inverse x equals some angle theta, so x is equal to tangent of theta. So if we label one of these sides as theta, tangent is then x, and tangent is opposite over hypotenuse, so we can label those sides like that. So then this side is the square root of 1 plus x squared, and then sine of inverse tangent of x, that's just sine of theta, and so that's just going to be opposite over hypotenuse, so this is x over the square root of 1 plus x squared. We'll do a similar thing if we have secant of inverse cotangent of y. So that triangle is going to start by saying we have inverse cotangent of y equals an angle theta. So y equals cotangent theta. So here we have a triangle. Cotangent is adjacent over hypotenuse. So we got y1. This side is going to be the square root of 1 plus y squared. And now that we have that, we need secant. Secant is 1 over cosine. So we have 1 over adjacent over hypotenuse. So that's just hypotenuse over adjacent. So that's going to be the square root of 1 plus y squared divided by y. Okay, so what's cosine inverse of cosine of 3 pi halves? We might think we can just cancel those and be left with 3 pi halves, but that's not the case. Remember that the outputs of inverse cosine are always between 0 and pi, so this is actually pi halves. And so the other one, inverse cosine of 4, that's saying what angle gives an output from cosine of 4? No such angle exists, so this last one actually does not exist. So pay attention to these inverse functions and be careful with these. If you didn't understand any of these, go back and check this section in your book. Okay, for our next one, let's start talking about limits. So I'm just going to write down a whole bunch of limits, and I'm going to ask you to figure out what they are. So, first one, we got limit as t approaches 7 of 3 to the t minus 5 minus 7 divided by t plus 2. We have the limit as t goes to 0 of the square root of t squared plus 9 minus 3 all over t squared. We have the limit as t goes to 0. Actually, this one's x. Limit as x goes to 0, sine of 7x divided by 2x. And then we got limit as x goes to pi halves from the right of tangent of x. Okay, go ahead, figure out all 4 of these limits. And actually, let's just throw one more in. Limit as theta goes to 0 of 10 over theta squared. Okay. So for this first one, if we just plug it in, we're not going to get any problems. This function is continuous at 7, so we can just plug it in. So that's going to be 3 squared minus 7/9. So that's our answer for our first one. This next one, though, this one is a 0 over 0, so we could use L'Hopital's rule, but if we're told we can't use L'Hopital's rule, we have to do this a different way. And the way we're going to do that is we are going to multiply the top and bottom by the conjugate of the top, meaning we leave the top the same, t squared plus 9 minus 3, leave the bottom the same, but then we're going to multiply the top and bottom by the exact same thing that we had on the top, except we changed the negative sign to a plus, and we're just going to do that on the top and bottom. So when we go through and do this, this is going to turn this first limit into the limit as t goes to 0 of, when we multiply the top, we get a t squared plus 9 minus 9, those plus and minus 9s cancel, over t squared times the square root of t squared plus 9 plus 3. Now the t squareds cancel, and so we are left with come on, move down. There we go. So what we are left with is the limit as t goes to 0 of 1 over the square root of t squared plus 9 plus 3. And now we can plug in 0, and we get this is 1 over square root of 9 plus 3. So this is 1/6. Okay, so this next one, we're going to need to have some properties that we remember. So remember, the limit of sine x over x, that goes to 1. So let's force this to have a sine of 7x over 7x. So this is equal to the limit as x goes to 0 of sine of 7x divided by 7x times 2/7. What we can do is now this piece, that is going to 1. So this is going to a 1 over 2/7. This goes to 7/2. All right, limit as x goes to pi halves from the right of tangent of x. This one, we're going to need to know what tangent of x is doing, and tangent of x does this. And these asymptotes happen at the pi halves, 3 pi halves, negative pi halves, and all of those odd multiples of pi halves. And so we are approaching one of these pi halves from the positive side. So that means our function is going down this direction, so this is negative infinity. And the limit as theta goes to 0 of 10 over theta squared. The bottom is getting really small but is always positive. The top is always positive, so this one goes to a positive infinity. If any of these didn't make sense, go back and study these a little bit more. Okay, so now that we have these, let's do some more limit problem stuff. Let's say that we know that the limit as x goes to a of f of x is equal to 5, and we know that the limit as x goes to a of g of x is equal to 2. What are the following? We got the limit as x goes to a of f of x all cubed. We have the limit as x goes to a of f of x minus g of x. We have the limit as x goes to a of g of x divided by f of x plus 3. We have the limit as x goes to a of the cube root of f of x plus g of x plus 1. Go ahead and compute these four limits. Alright, so the first one, this is just going to be 5 cubed. This one is 5 minus 2, so this one's 3. This one is going to be a 2 divided by 5 plus 3, so this is a 2/8, so this one's 1/4. And this last one is the cube root of 5 plus 2 plus 1, so the cube root of 8, so that's going to be a 2. If you didn't understand any of these, go back and study some limit laws. Okay, let's do some more limit stuff. clear. There we go. Okay, we got two more limits to figure out. What is the limit as h goes to 0 of 3 plus h cubed minus 27 divided by h? And what is the limit as x goes to 0 of x to the 4th sine squared of 3 over x plus 5? So figure out what these two limits are going to be. Alright, so for this first one, what we're going to do is we're just going to expand this all the way out. We got the limit as h goes to 0. Expanding the top out completely gives us a 3 plus h cubed. So let's expand that real quick. 3 plus h, 3 plus h, 3 plus h. That's going to be a 3 plus h times, we got a 9 plus 6h plus h squared. So expanding that will give us a 27 plus 18h plus 3h squared plus 9h plus 6h squared plus h cubed. So expanding all of that together, that gives us a 27 plus 27h plus 9h squared plus h cubed minus 27 all over h. So the 27s, those cancel. And then we can cancel an h from everything. And when we do that, we get this is the limit as h goes to 0 of 27 plus 9h plus h squared. We can plug in the h equals 0, and this term go to 0, so we are left with just 27. Okay, this last one, if you weren't able to figure this out, this one is going to be a squeeze theorem. So we are going to have to find functions that are both bigger and smaller than this. So a function that is always bigger, so we got x to the 4th sine squared of 3 over x plus 5. So sine squared is always between 0 and 1. So a function that's always bigger is going to be x to the 4th times 1 plus 5, because x to the 4th is always positive. And a function that's always smaller, sine squared is never smaller than 0, so a smaller bound is going to be x to the 4th times 0, so that's just 0, so a 5. So those are going to be the things that are between it. So this is going to satisfy the limit as x goes to 0 of 5 is less than or equal to the limit as x goes to 0 of x to the 4th sine squared of 3 over x plus 5, which is less than or equal to the limit as x goes to 0 of x to the 4th plus 5. Both ends go to 5, so this limit is also equal to 5. Okay, next question is involving continuity. So we might be asked, prove that f of x equaling 5 if x equals 2, and x squared plus x minus 6 divided by x minus 2 if x is not equal to 2 is continuous. Okay, so the way that we would do this problem, in order to show continuity, we need to show that the limit is equal to the value of the function at every point. Well, this part, that is continuous everywhere as long as the denominator isn't 0. So it's continuous everywhere that x is not equal to 2. The only point we have to check is the point x equals 2. So we're going to look at the limit as x approaches 2 of f of x. Well, this is all points that are not including 2, so that means we are only using the x squared plus x minus 6 over x minus 2 term. So this is the limit as x goes to 2 of x squared plus x minus 6 over x minus 2. So this is the limit as x goes to 2 of x minus 2 times x plus 3 divided by x minus 2. We can cancel because we are inside a limit. And now it's a function we can plug into, and we get 5, which is equal to f of 2. So that means that this function is continuous. Alright, so now let's do another problem. Let's look at what is the limit as x goes to infinity of 13x plus 5 divided by 8x squared plus 3x plus 2. And I'm going to ask you to do this without L'Hopital's rule. Let's go ahead, try and figure this one out, and then if you figure that one out, then try and figure out the limit as x goes to negative infinity of e to the x sine x, both of these without using L'Hopital's rule. Alright, so for this first one, what we're going to want to do is, if we just plug in infinity, we get infinity over infinity, which is one of those things we just don't know what it goes to. So what we're going to do is we are going to multiply the top and the bottom by 1 over the highest power of x that there is. And in this case, that's going to be a 1 over x squared that we multiply the top and bottom by. And if we do that, this turns into the limit as x goes to infinity of 13 over x plus 5 over x squared divided by 8 plus 3 over x plus 2 over x squared. And now as x goes to infinity, this term, this term, this term, and this term, those all go to 0. So we are left with just 0 over 8, which all goes to 0. Now how about this next one? The limit as x goes to negative infinity of e to the x sine x. Well, this first piece, e to the x, that's going to 0, but sine x is going between different numbers, so we don't know what it's going to yet. But this is actually going to be a squeeze theorem problem again. We know that e to the x sine x is always less than or equal to 1, so this is less than or equal to 1 e to the x. But sine x is also greater than or equal to negative 1, so it's always greater than or equal to negative 1 e to the x. And so then as we look at the limit of each of these pieces, so we have the limit as x goes to negative infinity, e to the x, that is less than or equal to the limit as x goes to infinity of e to the x sine x. Oh, I forgot a negative sign here. That is less than or equal to the limit as x goes to infinity of e to the x, just positive e to the x. Now, this side goes to 0, this side goes to 0, so that means that this limit goes to 0. Okay, let's do one more problem before we move on to the stuff that is on our second chunk of the material. So, I want you to prove that f of x equals e to the 12x plus 7x squared minus 5x plus 2, minus 5x minus 2 has a 0. So prove that this has a 0 somewhere. So the way that we're going to do this is going to be using the intermediate value theorem. So this means that we can show that if this function is continuous, then if there's a point where it's positive and a point where it's negative, then that means that somewhere it has to be 0. Well, let's just plug in some easy points. So f of 0, that's going to be e to the 0 plus 0 minus 0 minus 2. This is 1 minus 2. This is negative 1, which is less than 0. What we now need to do is we need to find something that's bigger than 0. Well, let's just try f of 1. Well, that's e to the 12 plus 7 minus 5 minus 2. That's e to the 12, which is bigger than 0. So that means that from these two pieces, by the intermediate value theorem, there is a 0. There might be more than one, but we just can guarantee that there is at least one. Okay, so this is all the material that was covered on the first test review that I did for this class. So moving on from here, we're going to now be talking about the stuff that was on the second test review. Okay, so let's jump into that. And this is where we start to talk about derivatives. Okay, so using the definition of the derivative, I want you to find f prime of 3 of the following functions. We have f of x, actually just this one function, f of x equals x squared, x squared plus 3x plus 1. Okay, so there's two different definitions of the definition of the derivative. We have f prime at a is equal to f of x minus f of a divided by x minus a, or it's f prime at a is equal to f of a plus h minus f of a divided by h. Oh, I forgot a very important piece. Both of these have a limit out front. So it's this one's the limit as x goes to a. This is the limit as h goes to 0. And both of these give us f prime at a. Okay, so let's do this problem using both methods. So this first one, this is going to be f prime at 3 as x approaches 3 of x squared plus 3x plus 1 minus f of 3. So f of 3 is 3 squared plus 3 times 3 plus 1. So that is 9 plus 9 plus 1. So that's a minus 19 divided by x minus 3. Let's zoom out a bit. This is going to be the limit as x goes to 3 of x squared plus 3x minus 18 divided by x minus 3. Fortunately, x squared plus 3x minus 18 factors, and we get the limit as x goes to 3 of x plus 6 times x minus 3 divided by x minus 3. X minus 3's cancel. The limit as x goes to 3 of that is 9. Okay, let's do the same thing but with this other situation. The limit as h goes to 0, so we got the limit h goes to 0 of 3 plus h squared plus 3 plus h plus 1 minus f of a, that's another minus 19, all over h. So we expand that out, we get the limit as h goes to 0 of 9 plus 6h plus h squared plus 3 plus h plus 1 minus 19 is minus 18. Okay. All over h. Oh, I forgot a 3 right here. There's a 3 right there, which means that these numbers are 9 and 3h. 9 plus 3h minus 18. So then this becomes the limit as h goes to 0 of 9 plus 9 minus 18. All of those cancel. So we are left with just h squared plus 9h divided by h. That's the limit as h goes to 0 of h plus 9, which is also 9. So in both cases, we're going to get the derivative is 9. Okay. Now, let's do the following. So using the definition of the derivative, what is f prime of x if f of x equals the square root of x and f of x equals 1 over x minus 2 and f of x equals 3x squared plus 5. Okay, so for each of these we're going to be using the definition. So it's the limit as h goes to 0 of f of x minus f of a, f of x plus h minus f of x divided by h. So we got that. So this is going to be the limit as h goes to 0 of the square root of x plus h minus the square root of x all over h. Now, as we had, I think, a little bit earlier, we're going to be using the conjugates to approach this one. So multiply the top and bottom of this by square root of x plus h plus square root of x over the square root of x plus h plus square root of x. This is a common technique anytime you have square roots in addition. And this will become the limit as h goes to 0 of x plus h minus x divided by x divided by h times square root of x plus h plus square root of x. So that's going to be equal to the limit as h goes to 0 of x plus h minus x, so that gives us just an h over h, square root of x plus h plus square root of x. The h's cancel, we're left with just a 1 on the top. And so when we plug in h equals 0, we get a 1 over 2 square root of x, which you can then check using your derivative rules that you know and love. I hope you love them. They are your friends, because we don't want to have to do this every time. Alright, this next one, limit, is going to be the limit as h goes to 0 of f of x plus h minus f divided by h. So this is going to be the limit as h goes to 0 of 1 over x plus h minus 2 minus 1 over x minus 2 all over h. Okay, at this top, let's combine those into a single fraction. So that becomes the limit as h goes to 0, stuff over h. Getting a common denominator gives us x minus 2 over x minus 2, x plus 2. So we have that, and we have minus the x plus h minus 2. A whole bunch of stuff can simplify down, and we get the limit as h goes to 0 of negative h divided by h times x minus 2, x plus h minus 2. H's can cancel, we're left with a minus 1 on the top. Plug in h equals 0, you get a negative 1 over x minus 2 squared. Now for this last one, we got the limit as h goes to 0 of f of x plus h minus f of x. So that'll be a 3x plus h squared plus 5 minus 3x squared plus 5 all over h. This is equal to the limit as h goes to 0 of 3x squared plus 6xh plus 3h squared plus 5 minus 5 minus 3x squared. Those will be canceled all over h. So this will be the limit as h goes to 0 of 6x plus 3h, which is just 6x, which makes sense from our derivative rules. Okay, now that we have this, let's quickly talk about some notation. So what does this mean? This means we take the third derivative of x. So f20, this is saying take the 20th derivative. So if you see an exponent of a function where it's in parentheses, that means take that many derivatives. Alright, let's now cover all of the different derivative rules. So, the derivatives of the following. So a constant goes to 0, x to the n, that goes to n, x to the n minus 1. A constant times a function goes to the constant times the derivative of the function. E to the x goes to e to the x. Sine x goes to cosine x. Cosine x goes to negative sine x. Let's see, we have f of x plus g of x. That goes to f prime of x plus g prime of x. F of x times g of x. This is the product rule. This is going to go to f prime of x g of x plus f of x g prime of x. You have f of x divided by g of x. This is going to be the quotient rule, so you get g of x, f prime of x, minus f of x, g prime of x, all over g of x squared. Chain rule, we have f of g of x. This goes to f prime of g of x times g prime of x. Let's see what other ones. Logarithms. We have natural log of x, 1 over x, and log base b of x, that goes to 1 over x times natural log of b. Oh, and also forgot base to an x, so b to the x, this goes to b to the x natural log of b. Alright, so those are the most common derivative rules that we will come across. So using these rules, what are the derivatives of the following 4 functions? We have x to the 7th minus e to the x plus x to the e plus natural log of x squared plus 5. We have x cubed plus 7x times e to the 5x plus 4 cosine of x. We have e to the minus e to the negative 5x divided by 4x squared plus sine of 2x. And then we have tangent of x divided by natural log of x plus 5. So figure out what each of these derivatives are. So for this first one, we're just going to go through piece by piece. So derivative of x to the 7th, that is 7x to the 6th. E to the x stays e to the x. X to the e, that becomes e times x e to the e minus 1. Natural log of x squared plus 5, that goes to a chain rule. So we have plus a 1 over x squared plus 5 multiplied by the derivative of the inside is a 2x. So that's the derivative of the first one. How about the derivative of the second? Well, this is going to be a product rule. So we have first times the derivative of the second times derivative of e to stuff is e to stuff multiplied by the derivative of the inside from the chain rule. So it'll be a 5 minus 4 sine x. So first times the derivative of the second plus the second times the derivative of the first. So derivative of the first is 3x squared plus 7. E to the 5x plus 4 cosine of x. Okay, the next one. This one's going to be a quotient rule. So we got low d high, 4x squared plus sine 2x. Low d high, derivative of the top is a 5e to the 5x minus negative 5e to the negative 5x. Low d high minus high, e to the 5x minus e to the negative 5x times the derivative of the bottom goes to an 8x. Derivative of sine is cosine, so we get a cosine 2x times the inside, so we get a 2 cosine 2x. So low d high minus high d low all over the bottom squared. There you go. And now the last one. This is another quotient rule one. So we got low d high, natural log of x plus 5, times the derivative of the top. If you don't know the derivative of tangent, you can get it by using the quotient rule. So, but the derivative of tangent is secant squared. So we got natural log x plus 5 times secant squared x minus high d low times derivative of what natural log of x plus 5 is 1 over x plus 5 times the derivative of x plus 5 is a 1 all over the bottom squared. And there you go. Those are all of those different derivatives. And there you go. That is us going through all the material on the second of my test reviews. Okay, let's jump into the stuff that was on the third test review. First one is implicit differentiation. So, for example, let's go through a few different problems that we might come across. For example, let's say that we have y equals arctangent of x. What is y prime? Well, arctangent is not one of those functions that we knew what we were able to do, but we can rewrite this function and then take a derivative. This is the same thing as saying tangent of y equals x, and we know the derivative of tangent, and we know the derivative of x, so we're going to just take the derivative of this using the chain rule. So the derivative of tangent goes to secant squared of y times the derivative of the inside, and that's equal to 1, so y prime is 1 over secant squared y. Now the problem is we just have given y prime in terms of y when we need it in terms of x. So we're going to need to solve for y in terms of x, and this is where we can go back to those triangle problems we were talking about earlier, where tangent of y equals x, so that means some angle is y, and the ratio of sides gives us x. So that'll be x and 1, this side will be the square root of 1 plus x squared. So secant, that is, well, y prime equals 1 over secant squared, that means y prime equals just cosine squared. And cosine is adjacent over hypotenuse, so that is going to be 1 over the square root of 1 plus x squared squared. So that's just a 1 over 1 plus x squared. So y prime is 1 over 1 plus x squared. Now we can do this with other sorts of situations, like if we have y equals the natural log of x, that means e to the y equals x. So then e to the y times y prime equals 1. Y prime equals 1 over e to the y. E to the y was x, so that's where we get the derivative of natural log is just 1 over x. Okay, now that we've gone through these two, let's go and do two problems that I'm going to ask you to do before I show you. First one, so in both cases you're trying to find y prime. So the first one is sine of 2x plus 3y equals y squared cosine of 5x. And the other one is going to be x to the 4th plus y to the 4th equals 81. Okay, so for this first one, let's go through and do it. We're just going to take the derivative of both sides r. So derivative of the first side, derivative of the sine is cosine, so we get cosine of 2x plus 3y times the derivative of the inside is a 2 plus 3y prime, and that's equal to the derivative of the other side is going to be a product rule, so we get a 2y y prime cosine of 5x plus y squared times derivative of cosine is a minus, so we get minus y squared sine of 5x times 5. And we are now going to try and solve for y prime. So we have a y prime here and a y prime here that we need to get alone. Everything else we want to move us to the other side. So when we do so, we are going to be left with a 3 cosine 2x plus 3y y prime minus the 2y cosine of 5x y prime is equal to, we're going to be moving the other pieces over, so we have a minus 2 cosine 2x plus 3y minus y squared sine of 5x times 5. So we can factor out this y prime term. So we factor out the y prime term, and then we can divide that term over. So we are left with y prime is equal to negative 2 cosine of 2x plus 3y minus 5y squared sine of 5x all over 3 cosine 2x plus 3y minus 2y cosine of 5x. And there you go. That's y prime in that first case. Now, let's go and do the second problem. Come on. There we go. So when we take the derivative of both sides, we get a 4x cubed plus 4y cubed y prime equals 0. So that means y prime is equal to negative 4x cubed over 4y cubed. So that's just negative x cubed over y cubed. What we might then be asked is, what's y double prime? Well, y double prime, just take the derivative of both sides again. So y double prime is equal to, this time it's the quotient rule, so we got low d high, so y cubed minus 3x squared minus high, so minus negative x cubed times the derivative of the bottom is a 3y squared y prime, all over the bottom squared, so that's y to the 6th. Now we can't leave this in terms of the y primes because we want it in terms of just x's and y's, but we already know what y prime is, so that means we can plug that in and we get y double prime is going to be negative 3x squared y cubed plus 3x cubed y squared y prime is a minus x cubed over y cubed all over y to the 6th, and there you go. You could simplify that a little further, but that's what we would do. Alright, let's do a related rates problem. So we are building a snowman by stacking 3 identical, perfectly spherical balls of snow going straight up. And the snowman is going to be melting in such a way that the surface area of the snowman is melting at a constant rate of 3 pi square centimeters per minute. And at the instant when the snowman is 120 centimeters tall, we are going to try and figure out how fast is the height of the snowman changing, and then also how fast is the volume changing. So the way we're going to have to do this is we're going to have to find equations that are going to connect height, surface area, and volume all together. So the surface area of a sphere is going to be 4 pi r squared. And since we have 3 spheres, that means our function of total area is going to be 12 pi r squared. And we are told that it's melting at a constant rate of 3 pi square centimeters per minute. So that means that we know that dA dt is equal to exactly 3 pi. So we are going to be taking our function a and going to take its derivative to get a dA dt. So if a is equal to 12 pi r squared, that means that dA dt is going to be, taking the derivative gives us a 24 pi r dr dt. So there we go. That's going to be our connection between dA dt and dr dt. Now we have to figure out what's the relationship between dr dt and the height. Well, if we look at the height of this, we have 1 radius, 2 radius, 3 radius, 4 radius, 5 radius, 6 radius. We know that our function h, so the total height, this is equal to 6 times r. So if we're trying to find the change in height, dh dt, that's going to just give us 6 dr dt. So we now have a connection between height and our area function. So we are going to try and go through and solve for what is dh dt. So let's go through and do this bit by bit. So we know that we have 3 pi, here, let's do this a little lower. So we know that we got 3 pi is equal to dA dt, which is equal to 24 pi r dr dt. So we need to solve for dr dt. So that means that dr dt is equal to 3 pi divided by 24 pi r. So this is a 1/8 or 1 over 8 r is going to be dr dt. So that means that dh dt is equal to 6 times 1 over 8r. So this is going to be a 3 over 4r. So if we know what the radius is, that'll allow us to be able to solve for what dh dt is. Now the nice thing is, we actually know we can solve for what the radius is, because we know we are looking at the instant when it is 120 centimeters tall. So if we go through and solve for that, we know that 120 is going to be equal to 6 times the radius, so radius is going to be equal to 20. So dh dt is 3 over 4 times 20, so 3/80 centimeters per minute. That is going to be what the dh dt is. So coming up here to our answer, the height is changing at minus 3/80 centimeters per minute. So now how about the volume? What's the connection there? Well, volume also has a function that we can use. We know that volume of a sphere is 4/3 pi r cubed So that means that dv dt is going to be equal to 3 times 4/3, so let's say 4 pi r squared dr dt. And we already found what dr dt was. Dr dt is this right there, 1 over 8r. So this is going to be equal to 4 pi r squared divided by 8r. So we can simplify this a little bit and we get just pi r over 2. So we then can take what we know r to be. R is 20. So this is going to be equal to pi times 20 divided by 2, or it's just 10 pi. And because the surface area is decreasing, we know the sign is also negative. So the volume is going to be changing at minus 10 pi cubic centimeters per minute. That is how fast all of those different pieces are going through and changing. So hopefully this was a helpful problem for related rates. If you need other videos that I've made. So now that we have this, let's move on and try and find some absolute maximums and minimums. So for this problem, you need to find the absolute maximum and minimum values of the function f of x equals x cubed plus 3x squared 15x plus 6 on the interval from -10 to 8. Alright, so the way that we're going to be going through and doing these is we have to identify where can we get maximum and minimum values. So the places that we have to check, we need to see where f prime of x equals 0 or does not exist. Those are both things that might give us an absolute maximum or minimum, and then also our boundaries. So our boundary, these are just going to be x equals -10 and x equals 8. Those are two places we're going to have to check. And the others, we're going to need to go through and solve for where f prime is equal to 0. So f prime of x, this is 3x squared plus 6x minus 15, which factors out a 3, and we're left with x squared plus 2x minus 5. And those values, if we don't see how we can factor this, which I personally don't, the way that we would have to go through and do this is we are going to go through and use the quadratic formula. So that says that our solutions are x equals opposite b plus or minus the square root of b squared minus 4ac all over 2a. So if we go through and use that, that means this will happen at x equals opposite b gives us a -2 plus or minus the square root of b squared. So 2 squared is 4, minus 4 times 1 times -5, all over 2a. So this is a -2 plus or minus the square root of 4 plus 20, so the square root of 24, all over 2. So this will happen at, let's see, we got a -1 plus or minus square root of 24. We can pull a 4 out, so that becomes a 2 square root 6 over 2. This is -1 plus or minus the square root of 6. So those, along with these values up here, those are the x values we have to test. So what we could do is we could figure out where these maximums and minimums by using the first derivative test or the second derivative test. If you don't remember those, check out one of those videos or go and look it up in the textbook. But all we care about are the absolute maximum and minimum values, so we just have to plug these 4 values into our function. So we're going to need to know what is f of -10, f of -1 minus the square root of 6, f of -1 plus the square root of 6, and then f of 8. So let's go through and look at what these different values are. So f of -10, that's going to be -10 cubed plus 3 times -10 squared minus 15 times -10 plus 6. So that is -10 cubed, that's a -1000 plus 300 plus 150 plus 6. So that is going to be pretty negative. let's see what exactly that is. So that's minus 700 plus 150, that's minus 550, minus 544. I hope that's right. I did that in my head. Next one, we're going to plug this in, so we get a negative 1 minus the square root of 6 cubed plus 3 times minus 1 minus the square root of 6 minus 15 times minus 1 minus the square root of 6 plus 6. We can expand all of those out, and we can go through and expand those multiplications. I'm just going to pull up my calculator and do it real quick, but this is an expansion that you would be able to do by hand. It's just a bit messy. So negative 1 minus the square root of 6 cubed plus 3 times negative 1 minus the square root of 6 squared. Whoops, I forgot that piece here. There's a squared right there. Let's see, then we have a minus 15 times negative 1 minus the square root of 6 plus 6. And if we go through and see what that all is, oh, forgot a parenthesis in my calculator, so let's go through and fix that real quick. And we expand that out, that becomes 12 square root of 6 plus 23, which square root of 6 is between 2 and 3, so that means this is around 24 plus 27, so that is about 53. So this is somewhere between 53 and 59. So this is about 56. And if we do the same thing, but instead of minus the square root of 6's, we have plus square root of 6's, it will go to a number that's probably pretty close, but let's go and see exactly what that is. That goes to 23 minus 12 square root of 6, which is about negative 7-ish. So the first one, let's actually write down exactly what that is. This first one's actually close to 52, a lot closer to 52. And then f of 8, this one is going to be one that we can go through and compute easily. 8 cubed plus 3 times 8 squared minus 15 times 8 plus 6. 8 cubed, that is going to be 64 times 8, which is 512, plus 3 times 8 squared. Let's see, so that's plus 3 times 64, which is, what, 180 plus 12, so that's 192. Let's see, 15 times 8, that's 80 plus 40, so that's minus 120, and then plus 6. So we add all of those up, and we get, let's see, and that goes to 590. So in this case, our absolute maximum and our absolute minimum happen at the endpoints, but we have local minimums and local maximums at other values as well. Okay, next one, let's do some mean value theorem stuff. So for the mean value theorem, is there a C value inside the region from 0 to 7 such that f prime at C is equal to 31 over 28 if f of x is equal to 3x over x minus 4. Go ahead, try and figure this one out. Okay, so remember the mean value theorem says that if we have a function that does something like this, and you take two endpoints and you connect them with a line, the slope of this line is going to be equal to the slope of the tangent curve somewhere else on the curve. So maybe at this point, the tangent line's parallel. Or here, same thing, or here, same thing. It says there's at least one point if a couple conditions apply. F has to be continuous and differentiable everywhere on the interval. The function f of x that we are given is not differentiable. The function f of x has a discontinuity at 4, which is inside our region here. So the answer is not by the mean value theorem. We can't guarantee it, but we might still have it still be the case, because we might have something like this, where we have a curve and there's still this point down here where the slopes match up, but we can't guarantee it. But what we can do is we can look at what's the derivative, and you find that f prime of x is going to be low d high, so that's a 3 times x minus 4, minus high d low, so minus 3x, all over the bottom squared. So this is negative 12 over x minus 4 squared. So the derivative is always negative. Here we're asking to see if it's somehow positive, and this is the value, the slope we would get connecting the 2 points at f of 0 and f of 7, but the mean value theorem does not guarantee anything. Now, how about a different problem? So this one, be sure to check, is this a trick question? So is there a c in the interval 1 to 5 where f prime of c equals 13 and f of x equals 3x squared, let's fix that, is equal to 3x squared minus 5x plus 2. Okay, using the mean value theorem, let's find the value of the slope connecting our two endpoints. So f of 5 minus f of 1 divided by 5 minus 1. So that'll be 3 times 25 minus 25 plus 2 minus 3 minus 5 plus 2 all over 4. Well, that goes to 0. So this other one goes to 75 minus 25 plus 2. So that's 52 over 4, which is 13. Okay, so the endpoints match, and our function is a continuous function. So the answer is yes, by the mean value theorem. Okay, if that didn't make sense, go back and study the mean value theorem a little bit more. Okay, next one. And this is a common question that you might see on a test. Show there is exactly one solution to the function f of x equaling 0 if f of x equals cosine of 3x minus 7x plus 5. Okay, how would we do this problem? So this problem is actually a combination of two different things. We have to use the intermediate value theorem to guarantee that there's at least one solution. So this is one or more solutions. And then we're going to use the mean value theorem to show that there is not two or more solutions. Okay, so the first part, intermediate value theorem. We need to find something that's bigger than 0 and something that's smaller than 0. So first part, f of, and then we're just going to pick points that we think are going to be nice. So maybe f of 0, well that's going to be cosine of 0 minus 7 times 0 plus 5. Cosine of 0, that's 1, so we end up getting 6, which is bigger than 0. Now we need something that's smaller than 0. So maybe we look at f of pi. Well, this is going to be cosine of 3 pi minus 7 pi plus 5. Cosine of 3 pi, that's negative 1. So we get negative 1 minus 7 pi plus 5. This is negative. So that means there is at least one solution. Okay, next part, how do we show that there is exactly one solution? This is where we're going to have to use the mean value theorem. So if there are two solutions, since f of x is both continuous and differentiable, what we have is we can use the mean value theorem. So the mean value theorem says that let A and B two different solutions. Then, in the interval from A to B, there is a C where f prime at C equals f of B minus f of A over B minus A equals 0. Okay, so that means there's somewhere where the derivative is equal to 0. But f prime of x equals, now we're going to need to take its derivative. So we zoom out to see our function again. Okay, our function is cosine of 3x, so the derivative of that is negative 3 sine of 3x minus 7. This is never 0. Because the only way for it to be 0 is if this was equal to positive 7, which would mean that sine of 3x would have to be 7/3, which is bigger than 1, which is impossible. So that means that this is never 0, so there is only one solution. We got a contradiction from our assumption, so that means there has to be only one solution. And that is how you would approach any of these sorts of problems. Alright, for our next one, we are going to try and graph a function. Okay, so we got a place to graph something, and we are going to have to graph a function that satisfies the following requirements. We have f of 1 equals f of 5 equals 3. We have f of negative 5 equals 0. We have f of 3 equals negative 4. We got f prime of x is positive on the interval from negative infinity to 1, unioned with 5 to infinity. F prime of x is negative on the interval from 1 to 3, unioned with 3 to 5. F double prime of x is positive on the interval from 3 to infinity. F double prime of x is negative on negative infinity to 3. And we have the limit as x approaches 3 from the left of f of x is equal to 1. Go ahead, pause the video, and try and graph a function that satisfies these requirements. So the first thing I would do is I would plot the different points that we know. So we know that f of 3, 1, 2, 3, is at negative 4. So 1, 2, 3, 4. We know it has to pass through that point. F of negative 5 is 0. 1, 2, 3, 4, 5. And then f of 1 is equal to f of 5, so 4 is at 3. So it passes through this point and this point. Okay, so we've gotten these things taken care of so far. Now we need to have f prime of x is positive from negative infinity to 1. So the way I would do this is I would lightly, with pencil, say, okay, from negative infinity to 1, is going to be positive, so it has to be increasing there. And then it's increasing after 5. And then it's going to decrease from 1 to 3. So it'll decrease 1 to 3. And then again, it'll decrease from 3 to 5. But here's 5, so I have to have it decreasing like that. So we're going to have some sort of discontinuity. Let's see, we got f double prime is positive. Actually, let's jump down to this limit one first. This one says the limit as x approaches 3 from the left goes to 1. So that means it's going to be getting close to this point right here. So it's going to have to connect up like that somehow. So we've gotten this taken care of, and we tentatively have those two taken care of. Now, the second derivative is positive. That means it's concave up. So it's going to be doing something like that. And then it's concave down on the other end, so it'll be doing something like that. If we include an open circle there and an open circle there, everything that's in purple should satisfy all of our requirements. So let's make it a little bit thicker. So our proposed graph is going to be this. We have jump down there, comes up there, passes through like this, and then goes up to infinity like that. So now that we have this, we think this satisfies everything. Just go back through and check that it satisfies everything, and you'll find that it does. That's the best way to go about doing these sorts of problems. Okay, and that concludes all the material that was on the third test review. Alright, for our next topic, we're going to do some stuff with L'Hopital's rule. So I'm going to ask you to figure out the following 4 limits. We have the limit as x goes to 0 of x minus 7 to the 5th divided by 4x to the 5th plus e to the x. We have the limit as x goes to infinity of x minus 7 to the 5th divided by 4x to the 5th plus e to the x. We have the limit as x goes to infinity of the natural log of 2x e to the negative 3x. We have the limit as x goes to 0 from the right of 1 over x minus 5 over x cubed. Okay, go ahead and figure out all 4 of these different limits and unpause the video when you are ready. Alright, so for this first one, what we're going to do is we're going to first see if L'Hopital's rule even applies. So if we were to try and plug in 0, we'd get negative 7 to the 5th on the top, which is a finite number, which means that this is not going to be an indeterminate form. So we can actually just plug in 0 and see what we get. So we get negative 7 to the 5th divided by, the bottom is 4 times 0 plus e to the 0, that's 1. So this is just negative 7 to the 5th. This first one we were able to evaluate directly. So just because it looks like it might be a L'Hopital's rule, you have to check to see if its indeterminate form works. Now if we were going to infinity, then this one is going to be infinity over infinity, so L'Hopital's rule applies. So we can use L'Hopital's rule to say, well, this is going to be equal to the limit as x goes to infinity of the derivative of the top, that's a 5 times x minus 7 to the 4th, times the derivative of the top of the x minus 7, which is a 1, divided by the derivative of the bottom, goes to a 20x to the 4th plus e to the x. And now if we plug in infinity, we still get infinity over infinity. So we use L'Hopital's rule again. And we get the limit as x goes to infinity. We now have a 20 times x minus 7 cubed times a 1 divided by 80x cubed plus e to the x. Still infinity over infinity, so we use L'Hopital's rule again. And we get 60 times x minus squared divided by 240x squared plus e to the x. And this process is going to continue another couple times, so let's move these down. So that's equal to, using L'Hopital's rule, The derivative of the top is 120 times x minus 7. Whoops, forgot limit. Limit x goes to infinity. Forgot that here too. So there should be a limit x goes to infinity right there. Divided by 2 times 240 is 480 x plus e to the x. It's still infinity over infinity. So we use L'Hopital's rule again, and we get the limit as x goes to infinity of 120 divided by 480 plus e to the x. This is no longer infinity over infinity, so we can evaluate. We get a number over infinity. This all goes to 0. Okay, next one. Okay, so this one is, if we plug in infinity, we get natural log of infinity, so that's infinity. E to the negative infinity, that goes to 0. So this is a 0 times infinity situation. So what we have to do is we have to first rewrite this in a form that we can use L'Hopital's rule. 0 times infinity can either go to 0 over 0 or infinity over infinity. If we move the e to the negative 3x down to the bottom, we get divided by e to the 3x. This is now infinity over infinity. We can use L'Hopital's rule. We get a 1 over 2x times 2 is the derivative of the top. Forgot the limit piece. Derivative of the bottom is a 3e to the 3x. Those 2's can cancel. So we are left with a 1 over limit as x goes to infinity. We have a 3x e to the 3x. The bottom's going to infinity, so this all goes to 0. There we go. How about this last one? This one's infinity minus infinity. So we first have to find a way to combine everything together. So why don't we first rewrite this so that we have a common denominator. So this is x squared over x cubed minus 5 over x cubed. So this is the limit as x goes to 0 from the right of x squared minus 5 divided by x cubed. Well, as we go to 0 from the right, this is now negative 5 divided by 0, and the bottom is always positive, so this is actually going to negative infinity, and we never actually needed to use L'Hopital's rule. But the rule is sometimes this form right here might have been a 0 over 0 or infinity over infinity case, and then L'Hopital's rule would have been necessary. Alright, let's move on to a couple optimization problems. And if you need more help with L'Hopital's rule, that's a topic that you can go back and study and figure out a little bit more on. Okay, so for our first optimization problem, let's say that we are given this word problem. We are trying to draw a rectangle inside of a circle. So we have a circle, and we are going to be drawing some rectangle inside of this. Whoa, let's change the size of that pen. Okay, so let's say that we have some rectangle that we are trying to draw inside of a circle so that all four corners lie on the circle. And if we know that the radius of the circle is r, then what is the largest perimeter of any rectangle that can be drawn? That's what we're going to try and figure out. So let's start by labeling the picture we have. So let's say that the two sides of the rectangle are x and y. So then that means that the perimeter is going to be 2x's plus 2y's. And this is what we're trying to optimize. Now the question is, what's the relationship between x and y? Well, we already know that going from the center to a corner is r, because that's the radius of the circle. But if we do the center to both opposite corners, then that's going to mean that this is going to be another r up here. So that means that we now have the relationship x squared plus y squared is equal to 2 times the radius squared. So x squared plus y squared equals 4r squared. And now that we have this, what we're going to be able to do is we can solve for one variable. So y squared is equal to 4r squared minus x squared. So that means that y is the positive square root of 4r squared minus x squared. And we can take this, and we can plug it in up here to then find that our perimeter function is 2x plus 2 times the square root of 4r squared minus x squared. And now we can take the derivative. Because r is a constant, we only have one variable. So we can take its derivative, and we get that is equal to 2 plus 2 divided by 2 square root of 4r squared minus x squared times a minus 2x from the chain rule. So now that we have that, we can simplify a little bit, and we want this to be equal to 0. What we can do from here is we now need to solve for what values of x make this true. So if we add this term over to the other side, we get 2 is equal to 2x divided by the square root of 4r squared minus x squared. And if we square both sides, the equality is still going to be true. So that means that we get 4 is equal to a 4x squared divided by 4r squared minus x squared. We could multiply this over to the other side and divide both sides by 4 first. So we are left with 4r squared minus x squared has to be equal to x squared. So 4r squared equals 2x squared. Means that x is equal to the square root of 2 times r. And now that we have this, we now know what x is. We can then solve for y, and it turns out that y will also be the square root of 2 times r. So now that we have all of those pieces, we can now figure out what's the largest perimeter. The largest perimeter is going to be 2x's plus 2y's. So the largest perimeter is going to be 4 times the square root of 2, r. And that is going to be the maximum perimeter of any rectangle, which we actually just showed the largest perimeter has to be a square. Let's now do another optimization problem, this time where we are trying to find the point on the line, the line y equals, let's do, how about 7x plus 2, closest to the point 1, 3. How would we do that? Go ahead, pause the video, and unpause it when you're ready. So the way I would start this is I'd draw out the line. So we have y equals 7x plus 2, and then we have the point 1, 3. That's going to be somewhere around here. And we are trying to find the point closest to the line. So that's going to be something like this, and we need to figure out what's that distance between those. So the distance between the 2 points is going to be equal to the square root of x minus x naught squared plus y minus y naught squared, where this point here is x naught, y naught, and this point up here is the point y. So we get, this is the square root of x minus x naught is 1, so that's a x minus 1 squared, plus y minus 3 squared. But the nice thing is we know what y is. We already have a formula for y, so we can just plug that in here. So the distance is going to be the square root of x minus 1 squared plus 7x plus 2 minus 3, plus 2, 3 squared. So there we go. And now we're trying to find the point that's closest, so it's going to be minimizing distance. So it's the derivative. Well, the derivative of a square root is 1 over 2 times the square root, 7x minus 1 squared, times the derivative of the inside. Well, derivative of the inside is going to be a 2 minus 1 times 1 plus 2 times 7x minus 1 times 7. And now all of these 2's end up canceling out. And now we're trying to solve for when is this equal to 0. Well, the denominator is never 0, so that means we only really have to look at when is the top equal to 0. So we're solving for x minus 1 plus 49x minus 7, that's equal to 0. So we got a 50x equals 8. So x is equal to 8 over 50, or 4 over 25, or 0.16, whichever one of those you prefer. And now that we have x, we now know what y is, because we already have this nice formula for what y is. So that means that our point y is going to be 7 times 4/25 plus 2. So that's going to be 28/25 plus 2. We add those together, that's 3 and 3/25. And all of that goes together to be a 3.12. And there we go. So our point is going to be the point let's do it in decimals. 0.16, 3.12. That is the point closest to the point 13. Okay, let's do a Newton's method problem. Okay, so for Newton's method, let's say that we have the following problem. If f of x is equal to x cubed minus x plus 2, using Newton's method, approximate a 0 using x1 equaling 1. So in other words, it's asking you to find x2, x3, and x4. Alright, so the way that we do Newton's method, remember, it's x sub n plus 1 is equal to x sub n minus f of x sub n divided by f prime of x sub n. So there we go. That's the form we're going to be using. So first things first, we're going to need to know what's f prime. Well, f prime of x is just going to be 3x squared minus 1. Okay, so if we're going to go through and do this, x2, that's going to be x1 minus f of x1 divided by f prime of x1. That's going to be 1 minus f of 1, 1 minus 1 plus 2, that's going to be a 2, divided by prime of 1, f prime of 1 is just 3 minus 1, so that's a 2. So x2 is going to be 0. Okay, next one, x3, that's going to be x2 minus f of x2 divided by f prime of x2. That's going to be 0 minus f of 0, that's 2. F prime of 0 is negative 1. So 0 minus negative 2, that's a positive 2. And then x4, that's going to be x3 minus f of x3 divided by f prime of x3. So that's going to be 2 minus f of 2, that's going to be 8 minus 2 plus 2, 8, divided by f prime of 2, that's going to be 3 times 4 minus 1, so that's 11. So 2 minus 8 elevenths, 2 is 22 elevenths, 22 minus 8 is 14, so this is 14 elevenths. And we could continue this process, but the numbers would just get uglier. But that's how you would do Newton's method and approximating the 0 using x1 equals 1. If this didn't make sense, or you're not entirely sure what Newton's method is doing, go back and study that a little bit more. Alright, so now let's go over a very quick overview of a bunch of different antiderivatives. So an antiderivative is a function where if we have f of x as our function, its antiderivative is a function big F, where big F prime of x is equal to little f of x. So let's just go through a bunch of different rules involving antiderivatives. So if you have a constant times a function, this will just go to a constant times the antiderivative of that function. If you have a function f of x plus a function g of x, this will go to antiderivative of your first function plus your antiderivative of your second function, and this will work if it's plus or minus. You just keep the appropriate sign there. Let's see, what else we got? We got x to the n. The antiderivative of x to the n is x to the n plus 1 divided by n plus 1 plus c. If n is not negative 1. If n is negative 1, then that's 1 over x. The antiderivative of this is natural log of x plus c. Let's see, we got e to the x goes to e to the x plus a constant. We got b to the x. That'll just go to b to the x divided by the natural log of b. Let's see, we got cosine of x. Antiderivative of cosine of x is sine of x plus c. Antiderivative of sine of x, that is negative cosine of x plus c. If you got secant squared x, the antiderivative of that is tangent x plus c. Antiderivative of secant x times tangent x, that is going to be secant x plus c. And that's just a list of some common ones. If we are asked to try and do some different area approximations, this is a problem that you might come across. If you have 8 subintervals and you're trying to find the area under the curve y equals x squared, but above the x-axis, on the interval -1 to 3. If you were asked to do this using left endpoints, you would first need to divide up the interval -1 to 3 into 8 pieces. Well, that interval has length 4, so we're going to have 8 pieces. And then we're going to evaluate the function at each of these different points. So this one would be a 1/2 times f of -1 plus a 1/2 f of -1/2 plus a 1/2 f of 0 plus all the way up to a 1/2 f of 2.5. And if we were to write this as a sum, this would be the sum from I equals 1 to 8 of a function f of -1 plus I minus 1 times 1/2 multiplied by a 1/2, where each of these pieces, this is f of x sub I delta x sub I. And so that's how we would write our left endpoint form, and you would be able to add all of those things up together to figure out what is that going to be. And if you were to do this using right endpoints, instead of adding up the ones that are on our left endpoints, we would be starting at f of -1/2, so that would be a 1/2 f of -1/2 plus 1/2 f of 0 plus 1/2 f of +1/2 plus all the way up until you got a 1/2 f of 3. And if we were to write this as a sum, this would be the sum from I equals 1 to 8 of f of -1 plus I times a 1/2 times 1/2, where this is again the sum of f of xi delta xi. And that's how you would be able to go through and do this. You'd be able to add all of those up together, and that's how you would approximate this area without using a definite integral. Now, how would we evaluate this sum? Well, that's going to connect into how we would be able to do a bunch of different things. So for example, you might be asked to evaluate the following sums. Evaluate the sum from k equals 7 to 12 of 2k minus 3. So this is just going to be plugging in 7, 8, 9, 10, 11, and 12 and adding them up. So this will be 2 times 7 minus 3 plus 2 times 8 minus 3 plus 2 times 9 minus 3 plus 2 times 10 minus 3 plus 2 times 11 minus 3 plus 2 times 12 minus 3. So that's going to be 11 plus 13 plus 15 plus 17 plus 19 plus 21. And if we add these up, let's see, those add to 32, those add to 32, those add to 32. That's 32s, so that's 96. If you didn't notice that, you could just add them all up together, and they would work out nicely. And so our answer would be 96 in this case. But we might be asked something slightly different, like what is the sum from I equals 1 to n of 2i plus 1 times 4i squared minus 3. Well, this case, what we're going to have to do is we're going to expand this out. We multiply everything all the way through. We get an 8i cubed, let's see, plus 4i squared, minus 6i minus 3. So we're adding all of that up. And if we go through these pieces, we can break this up, and we get 8 times the sum from I equals 1 to n of I cubed, plus 4 times the sum I equals 1 to n of I squared, minus 6 times the sum I equals 1 to n of I, minus 3 times the sum I equals 1 to n of 1. This piece is important. You need to include this sum here at the end. Otherwise, you're going to probably mess up by forgetting that it's not just minus 3 at the end, but that is going to be a piece altogether. And if we go through and add all these pieces up, this first one goes to 8 times n plus 1 over 2 squared. We then have a 4 times n plus 1 2n over 6. We have a minus 6 times n plus 1 over 2, and a minus 3 times n. That's what each of those sums go to. And you can try and combine everything together to see what it all simplifies down to. But that's probably about as good of a form as you can. Maybe simplifying a little bit, like this 6 and this 2 can become a 3. The 4 and that can become a 2/3. 8 and the 2, that can become a 4. Those simplifications, but then other than that, that's probably the best that you're going to be able to do. So now that we've talked about sums a little bit more, let's go over definite integrals. So, using the definition of the integral from a to b of f of x dx, evaluate the following. Evaluate the integral from 1 to 4 x squared plus x plus 2 dx. How would we do that? Well, remember, the definition of an integral is going to be the limit, as n goes to infinity, of the sum I equals 1 to n, f of I delta xi, and what we're able to do is we are able to say that delta xi is always going to be b minus a over n, and xi, we can always use our right endpoint. This is one of the theorems that we are able to use. Our right endpoint is always a plus I delta xi. So what we can do is we can now plug these different things in for what we have. So this is going to be equal to the limit, as n goes to infinity, of the sum I equals 1 to n of f of xi. Xi starts at a, so that's going to be a 1, plus I times delta xi. Well, what is our delta xi? Well, that's b minus a over n, so that'll be a 4 minus 1 over n, so we'll have a plus 3i over n, and times delta xi, that's times a 3 over n. So we expand that all out, we get the limit n goes to infinity of the sum from I equals 1 to n of, we got a, 1 plus 3i over n squared plus a 1 plus 3i plus 2 times 3 over n. So we've gotten that much. Okay, what we want to do now is we're going to want to expand all of those pieces out. So we got this is the limit as n goes to infinity of, let's see, multiplying, sum I equals 1 to n of, let's see, 1 plus 3i over n squared, that goes to a 1, plus 6i over n, plus 9i squared over n squared, plus 1 plus 3i, that's an over n there, over n, and then a plus 2 times 3 over n. That becomes the limit as n goes to infinity of the sum I equals 1 to n of 1 plus 1 plus 2, that goes to a 4. So we got 4 plus the I over n's, we have 9i over n's, and we have a 9i squared over n squared, all times 3 over n. So that becomes the limit as n goes to infinity of the sum from I equals 1 to n of 12 over n plus 27i over n squared plus 27i squared over n cubed. And now we can break this sum up into multiple pieces. We have the limit as n goes to infinity of, we have a 12 over n times the sum from I equals 1 to n of 1 plus a 27 over n squared sum from I equals 1 to n of I plus a 27 over n cubed sum from I equals 1 to n of I squared. We know what each of those sums are, so we can evaluate that. So that becomes the limit as n goes to infinity of 12 over n times n plus 27 over n squared times n plus 1 over 2 plus a 27 over n cubed times n plus 1, 2n plus 1 over 6. So we got all of that. Now we just need to evaluate this. Well, fortunately, most of these are pretty straightforward. Those n's will cancel. This one we can use a L'Hopital rule on, because the top will be 27n squared, the bottom's 2n squared, and we can show that that'll go to a 27 halves. And then this last one is going to go to a 27 times 2 times n cubed over 6n cubed. Again, you can use L'Hopital's rule, and this whole piece will go to 27 times 2 divided by 6, which is 9 times 2 over 2, which is just 9. So we add all of these up, and that is our final answer. It is 21 plus 27 halves. Let's see, 27 halves, that's 13.5, so that becomes 34.5. That is our final answer. Okay, so now that we've done these, let's go over a bunch of properties of definite integrals real quick. So some different properties of definite integrals are that the integral from a to b of a constant dx, that's just the constant times b minus a. We got the a to b of f of x plus or minus g of x dx equal to the integral from a to b of f of x dx plus or minus the integral from a to b of g of x dx. So we got that. We have the integral from a to b of a constant times a function f of x dx. This is equal to the constant times the integral from a to b of f of x dx. We have the integral from a to b of f of x dx is equal to the integral from a to c of f of x dx plus the integral from c to b of f of x dx, and you can use that to go either direction. And then our last one is if we have that f of x is always less than or equal to g of x on the interval from a to b, then the integral from a to b of f of x dx is less than or equal to the integral from a to b of g of x dx. Alright, now let's talk about the fundamental theorem of calculus. So using the fundamental theorem of calculus, let's do the following 5 things. So first, find the derivative with respect to x of the integral from 7 to x of log of t minus 3t squared plus secant of t dt. Find the derivative with respect to x of the integral from x to 2x of e to the t natural log of t dt. Find the integral from 3 to 7 of x squared plus 5x plus 3 dx. Find the integral from 2 to 13 of e to the x plus x to the e dx. And find the derivative with respect to x of the integral from 7x minus 3 to sine of x plus pi fourths of natural log of t minus 5 over t squared plus 1 dt. Go pause the video and figure out these 4 integrals. 5. I can count. I majored in math. I should be able to count. Okay. Hopefully you had enough time. If you didn't, pause the video and make you have enough time. And let's go through and do these one by one. So this first one is just a direct application of the first part of the fundamental theorem of calculus. The fundamental theorem of calculus says if you have an integral from a constant to x, the derivative with respect to x is just going to be replacing all of the t's with that x value. So this is going to be natural log of x minus 3x squared plus secant of x. That is what the first one is going to be. The second one is a little bit trickier because it's not constant to variable. This is variable to something that is still a function. So we're going to have to break this up using some properties of definite integrals. So this is equal to the derivative with respect to x of the integral from x to some constant of e to the t natural log of t dt plus the integral from that same constant to 2x of e to the t natural log of t dt. So once we have this, what we can do is we can be able to approach the problem from here. So let's give ourselves some space. So this is going to be equal to, well, this first one is still not quite in the right form, so we're going to have to switch the order of integration, or bounds, to be constant to x, and if we do that, we have to introduce a negative sign. So then we got e to the t ln of t plus the integral from constant to 2x of e to the t ln of t dt. Now for each of these pieces, we can now use the fundamental theorem of calculus. So this first one is going to go to a negative e to the x ln of x. But then the other one is going to be replacing all of the t's with 2x, e to the 2x ln of 2x, but then we have to multiply by the derivative of the 2x. So we're going to get a 2. So that's what this one is going to be. Now how about these ones here? Integral from, let's see, let's get all of that in. There we go. A little bit more space. Okay, this one, the second part of the fundamental theorem of calculus says that we can just find an antiderivative and evaluate it at the endpoints. So the way we would do this is we need to find first what is an antiderivative. Well, x squared, that'll go to x cubed over 3, and then 5x goes to a 5x squared over 2, and then the 3 goes to a 3x. To evaluate this at 3 and 7. So going through the pieces of this, this is going to be equal to, we have 7 cubed over 3 plus 5 times 7 squared over 2 plus 3 times 7 minus 3 cubed over 3 plus 5 times 3 squared over 2 plus 3 times 3. And whatever that number is going to do. So let's go through and multiply all of those things out. I'm going to just use a calculator to figure that out. You would just have to do these by hand. So we got 7 cubed divided by 3 plus 5 times 7 squared divided by 2 plus 21, and then all of that minus 3 cubed divided by 3 plus 5 times 3 squared divided by 2 plus 9, and all of that together goes to 652 thirds. or 217 plus 1/3. And that's what this value would end up going to be. Now how about this next one? How would we do this? Well, this next one's the same process, it's just different function. So we still need to find an antiderivative. Well, this is going to be antiderivative of e to the x, that's just e to the x. Antiderivative of x to the e, that's x to the e plus 1 divided by e plus 1. And we evaluate this between 2 and 13. So this one's going to be e to the 13 plus 13 to the e plus 1 over e plus 1 minus an e squared plus 2 to the e plus 1 over e plus 1. And that's going to be our final answer because none of those are going to combine nicely. So that's how we're going to leave it. Now how about this last one? This last one you can either do by doing it a similar process to what we did with our second integral up here, or what we can do is we can use a combination of the first and second pieces of the fundamental theorem of calculus. We can say that this is going to be the derivative with respect to x of some unknown antiderivative of that function at sine of x plus pi fourths minus that same unknown antiderivative at 7x minus 3. Well, this is using the second piece of the fundamental theorem of calculus. So then we can use the first piece of the fundamental theorem of calculus to say that the derivative of big F is just going to be little f again. So we got little f of sine of x plus pi fourths times the derivative of the inside from the chain rule. So derivative of sine is cosine. So we got a cosine of x plus pi fourths. But then the derivative of x plus pi fourths is 1. So that's the end of the first piece, minus the function at 7x minus 3 times the derivative of 7x minus 3, which is a 7. So now we can go through and replace f with what it is. So this is going to be, let's see, natural log of sine of x plus pi fourths cosine x plus pi fourths minus 5 divided by, we got a sine squared of x plus pi fourths plus 1, and then multiplied by cosine of x plus pi fourths minus our function times 7, so we got minus 7 natural log of 7x minus 3, and then minus negative, so 5 times 7 is going to give us 35 over 7x minus 3 squared plus 1. And that is going to be this derivative. So we're able to combine them and rewrite them a little bit to be able to get nicer problems. Okay, so now that we have this one, let's do some problems that are related to this. Let's say that you know that f double prime of x is equal to 3x plus 2e to the x, and then we know that f prime at 0 is 7, and f of 0 is negative 4. What is f of x? Okay, so the way that we're going to have to do this, pause it if you want to try it first. So the way we need to do this is we need to figure out first what's the relationship between f and f double prime. Well, f double prime is two derivatives, so to undo that we're going to need to take two integrals. So first let's figure out what's f prime of x. Well, that's the integral of f double prime of x dx. So this is using like indefinite integrals and the relationship between integrals, antiderivatives, and all of that. So this is going to be the integral of 3x plus 2e to the x dx. Well, integral of 3x goes to a 3, whoa, go back. Okay, so integral of 3x is a 3 halves x squared. Integral of 2e to the x is 2e to the x plus some constant. But we know that if we plug in 0, we can solve for that constant. So f prime at 0 is equal to 7 but that's equal to 3/2 times 0 squared plus 2e to the 0 plus c. So that means that c has to be 5. So we can then say, well, what's f of x? Well, that's the integral of f prime of x dx. So this is the integral of that's the integral of 3/2 x squared plus 2e to the x plus 5 dx. Now that we have that, we can go through and evaluate this, and that'll be 3/2 x cubed over 3, so that becomes just a 1/2 x cubed plus 2e to the x plus 5x plus some unknown constant d is f of x. But we know that f of 0 is -4, and that's a 1/2 times 0 cubed plus 2e to the 0 plus 5 times 0 plus d. So that term goes to 0, that term goes to 0. We have -4 equals 2 plus d. That means that d is -6. So our function is going to be f of x is equal to x cubed over 2 plus 2e to the x plus 5x minus 6. And that's how we would do this problem. Alright, so now this is the end of the stuff that was on test review number 4. I'm now going to cover the last 2-3 topics that are going to be on this test, and then we're going to be done. So hang in there, we're almost done, both with the class and the review and all of this stuff. So hang in there, we're almost done. Okay, so the last couple topics, one of them is the net change theorem. So the net change theorem says that the integral of f prime of x dx from a to b, this is just f of b minus f of a. Doesn't feel super crazy. This is basically just an application of the fundamental theorem of calculus. So a problem you might have is something that might say like this. So if your acceleration is a constant minus 32 feet per second squared, what is your height at t equals 10 if your velocity is 0 feet per second at t equals 0 and your initial position is 20,000 feet. So this is extreme skydiving. So the way we would approach this problem is actually using the net change theorem. We know the relationship between acceleration, velocity, and position. They are all derivatives of each other. So what we can do is we can figure out, if we need to know what is our height, that's going to need to first figure out what's our velocity. So we can go through and figure these different things out piece by piece. So velocity as a function of time, this is going to be the integral of your acceleration. So velocity is the integral of -32. And that's all we have. So that means that velocity is going to be -32t plus some constant. But we can figure out what that constant is. Our initial velocity is 0 when t is 0, so it turns out that this is just -32t plus 0 in this case. It won't always be, but in this case it's plus 0. So now we can figure out what is our position at time 10. Well, if we rearrange the net change theorem just a little bit, we can find that f at b is equal to the integral from a to b of f prime at x dx plus f of a. So what we're really doing is we're trying to figure out how much did we change in position plus how much position did we already start with. So in this case, what we have is f, so our position at time 10, that's going to be the integral from when did we start, t equals 0, to when did we stop, t equals 10, of the derivative of position, that's just our velocity, plus our position at 0 when we start. So we can go through and figure out all these different pieces. So p of 10 is equal to the integral from 0 to 10 of minus 32t dt plus p of 0 is 20,000. We put all of this together. What's the integral of negative 32t? Well, that is going to be negative 16t squared evaluated from 0 and 10 plus 20,000. So p of 10 is going to be minus 16 times 100 minus negative 16 times plus 20,000. And we put all of that together and we get p of 10 is equal to 20,000 minus 1,600. So this is going to be 18,400 feet. So that is how high above the ground you are 10 seconds after you jumped out of the airplane. Why you would jump out of the airplane, I don't know. I'm terrified of heights, but you could do it, and this is exactly what you'd be thinking through in your head as you are falling to your death. Okay, so now that we have this one, let's talk about our last topic, which is U-Substitution. So U-Substitution, I'm just going to write up a whole bunch of different problems. In fact, I'm going to write 5 different integrals that you should be able to figure out by doing U-Substitution. So here they are. Substitution. That is not how you spell substitution. Let's fix that real quick. Might as well spell as well. Substitution. Okay, that's why I didn't go into English. Okay, so U-Substitution. Find the integral of natural log of x over x dx. The integral of, let's see, we got 38 sine of 19x squared plus 3 pi over 8 x dx. We have the integral of tangent x dx. We have the integral of secant to the 5th x tangent x dx. We have, and last but not least, 13 t to the 5th. I need to rewrite that a little bit. Last but not least, we got 13 t to the 5th over e to the t to the 6th plus 14t dt. Okay, go ahead, pause the video, and figure out these 5 integrals. Okay, so for this first one, we're going to want to figure out what is the piece that is the hardest for us to deal with. Well, I don't know about you, but I always struggle when I have a natural log of x inside an integral. So we are probably, for this first one, going to say that u is equal to the natural log of x. So if u is the natural log of x, what is du? Well, that's going to be the derivative of the natural log of x. So it's a 1 over x times dx. So now we can rewrite this integral as the integral of u, and then notice that this dx over x, that's the du. So we have integral of u du, which is equal to u squared over 2 plus c, but we can't leave it in terms of u. That's sort of like if you are assigned an English paper to write and you turn it in Tagalog. That's not going to be accepted. So you're going to need to retranslate this back into the language or the variables that you were asked to give it in. So you replace all of the u's with what they are. So that's going to be natural log of x squared over 2 plus c. And that is going to be the integral of this first function. Okay, how about this next one? What do we want to choose to be u? Well, the way that I normally do u's is I figure out what is the ugliest piece, and we're going to try and make it pretty. So this 19x squared plus 3 pi over 8, that's just an absolute mess. So I'm going to say that that is my u in this case. 19x squared plus 3 pi over 8. And if that's the case, what's my du? Well, derivative of 19x squared, that's 38x. And then the 3 pi over 8, the derivative of that is 0. So I'm looking to see if I can pull out a 38x dx. Well, here's a 38x dx. Perfect. So this is going to be equal to, we have the integral of sine of u du. So we can put all of this together. What's the integral of sine? Well, this one's one of those ones that I always get confused. But if you can remember, derivative of sine is cosine. Derivative of cosine's negative sine. That means negative sine goes to cosine, so positive sine will go to negative cosine in the integral. So this is going to be negative cosine of u plus c. So we have to replace the u with the appropriate variables. So we get negative cosine of 19x squared plus 3 pi over 8 plus c. And that's how you would do this problem. How about integral of tangent x? How would we do that? Well, to do this, what we're going to have to do first is rewrite the integral so that we can be able to pick a u. So if we rewrite this as tangent is sine x over cosine x, in this case, what's the ugliest piece? Well, it's the fact that we have this cosine in the bottom. So I am going to want to say that u is cosine of x. And if u is cosine of x, then what's du? Well, derivative of cosine is negative sine dx. So that means that this is going to be cosine. We're going to keep that in the bottom, so we have an over u. But then the sine x dx, that almost matches up. We just are off by a negative sign, so we replace that with a negative du. So this is asking, what is the integral of 1 over u du? Well, that's one of those that we know, so that's negative natural log of u. Well, natural log of u, that's going to be natural log of cosine. So negative natural log of cosine of x plus c. And you can also rewrite this using some log rules as being natural log of secant x plus c. And there you go. That's how you would be able to do this problem. How about this next one? Secant to the 5th tangent x dx. What is that going to be? Well, for this one, we might just try a couple and see what happens with them. So if we say that u is tangent x, then du is going to be secant squared x dx. Well, we have tangents, we have secants, so let's see what this would do. This would turn into the integral of u from the tangent x. Then 2 of the secants can go into the du. So we got secant squared x dx. That all goes together. But we're still left with secant cubed. This we somehow have to turn into u's, which is possible but is not pretty. So this is probably not the right choice to be able to simplify this down a ton. It is possible, but it's probably not the prettiest choice. So if we go through and try, instead of tangent, maybe we try secant. So if u is secant x, then what's the derivative of secant? Well, that's going to be a secant x tangent x dx. So now when we take out our du, that's going to be the tangent along with one of these secant x's, which leaves secant to the 4th x. So we're left with secant to the 4th x. So this is going to be u to the 4th. This is something we can do. So this is going to be u to the 5th over 5 plus c. We can replace the u with secant. So this is secant x to the 5th over 5 plus c. That is how we would do this problem. How about this last one? If we make a substitution, it's going to just mess up both pieces, but what we can do is we can rewrite this first as the integral of 13t to the 5th over e to the t to the 6th dt plus the integral of 14t dt. This one we can just do by itself to just give us a 7t squared plus c. But then this one, we're going to have to do some sort of U-substitution on that. And on this one, what's the most complicated piece? It's the fact we have a t to the 6th inside an exponent. So we'll probably say that u is just t to the 6th. So then du is going to be a 6t to the 5th dt. Okay, we have t to the 5th dt, but we don't have the 6. So how are we going to get that? Well, what we can do from here is we could solve for the t to the 5th dt, and that is equal to du over 6. So now what we can do is we can turn this into the integral of, we have a 13 that didn't do anything, over e to the u, and then what do we have left over? We have a t to the 5th dt, so that's times du over 6. We can pull the 13th 6 out, and then it's the integral of e to the negative u du. Okay, what are we supposed to do with this? Well, this is not one of those things that we remember exactly. It's close. If it was just e to the x, that would be great. But it's not. So what can we do? Well, we can do another U substitution. So we are doing a double U substitution, so W. So if we say that W is negative U, then dW, that is too many bumps, dW is going to be a negative du. So what we can do is this turns into a 13 over 6 integral of e to the w dw with a negative sign. This goes to a negative 13 sixths e to the w, which when we replace the e to the w, plus some constant. When we replace the w, that becomes negative 13 sixths e to the negative u, and then when we replace the u, that becomes negative 13 sixths e to the negative t to the 6th, plus d plus d. So our final answer is going to be this plus this. So this is equal to negative 13 over 6e to the t to the 6th plus 7t squared plus c plus d. Well, these are just two unknown constants, so the convention is just to combine them both together and call it a single constant. And so that is our final answer. Okay, congratulations everybody. You made it through both the test review, the class. If there were any topics you didn't understand, go back and study those topics. If you felt good on all of them, then don't worry too much about those problems. Maybe do one practice problem and see if you're still feeling confident with it. But if you're feeling good on all of these topics, you're probably prepared for your test, and you can be able to go and do it. If there's a couple topics you didn't quite understand, go back and study those some more, either from your practice problems, previous tests, previous videos that I've made on this channel. Feel free to check any of those out. But I wish you all the best of luck. Good luck on your test, and good luck with all of your future math classes. I hope you all have a wonderful rest of your day, and good luck with all of your math.